Okay, in this relatively short video here, we're just going to look at some of the reactions that ethers do. And we're going to find that there aren't very many of them because ethers are the least reactive of all oxygen-containing functional groups. All right, so the first one we're going to look at here is not a really selective reaction. It's just something to caution you about when you deal with ethers. If an ether sits out in the air for a very long time, it's going to undergo an autooxidation reaction. Okay? And in this autooxidation reaction, we're taking oxygen, which, remember from general chemistry, is a diradical like that. And it forms this type of compound called a hydroperoxide. And this is an explosive type of compound. Basically, this oxygen-oxygen bond here is very weak. Its bond association energy is only 35 kilocalories per mole. So mild heating or hitting it with a hammer or something like that can really detonate an ether. And this is something that you have to be aware of when you deal with ethers. So expiration dates and use by dates are very important with ethers. Okay? All right, so let's look at the main reaction here, and this is acid cleavage. All right, so if we have an ether, and we're going to have two different R groups on our generic ether, shown here, and we treat it with either HI or HBr, usually not HCl, and it's very important also that we don't have any water in this reaction. Okay, so we're treating it with the gas. Okay, so HI or HBr react with an ether to make an alcohol and an alkyl halide. And recognize that if the ether is unsymmetrical, there's two different products depending on who gets the halide and who gets the OH group. Okay, and if you use a large excess of HI or HBr, a reaction that you saw a long time ago, alcohols reacting with HX is going to occur also, and you're just going to get 2 moles of 2 different alkyl halides if your starting ether is unsymmetrical. Okay, so how do you know who gets who? Okay, rule number 1 is that the halogen ends up on the R group that's best able to do the SN2 reaction. By the way, this is added as a gas, but it can be done in other solvents that are not water or not ethanol or that don't have water or OH groups in them at all, like acetonitril and benzene and things like that are okay as solvents. Okay, so we're going to take this unsymmetrical ether, ethyl isopropyl ether, react it with 1 mole of HI, and what we'll find is that we get ethyl iodide and isopropyl alcohol. All right, so how does this occur? Well, we're just going to protonate it. Okay, so ethers have lone pairs, just like alcohols do, and the mechanism is really the same as that reaction you had a long time ago where alcohols react with HX to make alkyl halides, okay? All right, so this is going to give us now the protonated ether. What happens now is in the second step of this process, an SN2 reaction occurs. This carbon is primary. This carbon is secondary. We've known for a long time ago that SN2, that methyl is favored over primary, favored over secondary. Much better than tertiary. So the SN2 reaction is going to favor displacing the group off of the primary carbon. So I minus does like so, and that gives us the ethyl iodide. Okay, the only exception to this rule is if we have an exceptionally stable carbocation intermediate. And then we're going to see an SN1 mechanism take over. All right, so in this case, we have a primary group on this side and a tertiary group on this side. Okay, so we're going to treat with 1 mole of HBr, and what we're going to find here is that we get tertiary halide and the primary alcohol. The reason this is going the opposite way of the other one is because once we make the protonated alcohol, okay, it's going to leave in an SN1 type reaction, and this is because we can form this really stable tertiary carbocation. And in the last step, and this is the fast step of the reaction, the ethanol is just going to add, and we're going to, not adding the ethanol, we're adding the bromine, yeah, the bromine's going to add, and that's going to give us the product. Okay, so in this one here, we're going to work on a couple problems. What's the product from this, from each of these reactions? All right, so we're going to treat this one with HI. Okay, so the protonation is going to occur. We have to now think about what's better, SN2 at a primary carbon or SN2 at a benzene ring. Okay, we already know from many examples that we don't do SN2 reactions at sp2 carbon in most cases, so we're going to say that this is the only pathway that we're going to observe here, and our product should be, I didn't mean to draw it over where I was going to draw it there, but our product is going to be this one, where the iodine attacks exclusively at the primary carbon. Okay, this is the only product you're going to get. It doesn't matter how much HI you add. If you add 1 mole, 2 moles, you'll never add more than 1 mole to this compound because you can't do an SN2 displacement of this group right here. You can't do an SN1 displacement either because a phenylcation is not a stable carbocation. All right, so what starting material would react with excess HBr and give us methyl bromide and this bromide right here? Excess, I guess, would be greater than 2 moles. All right, so what is our starting material here? Well, it has to be an ether with a methyl group and that group that's attached to bromine on it, and that is the logical starting material for that investigation. Okay, all right, so let's just, I'm going to end this talk with this slide here, but we have various cyclic ethers, and as long as there's not significant angle strain, there's really not any difference in the chemistry of cyclic ethers and non-cyclic ethers. Okay, so the ether in a 5-membered ring is called Tetrahydrofuran, which has this abbreviation here. You've probably seen it many, many times. Okay, the cyclic ether with 2 oxygens in a para relationship is called 1,4-dioxane. These are very common solvents. If we wanted to describe the reactivity of tetrahydrofuran or 1,4-dioxane, we can just say it's just like any other ether. Okay, this is another ether that we've looked at a long time ago, furan, and we looked at how one of the lone pairs contributes to the conjugation with the other alkenes, and ultimately we have an aromatic 6-pi electron system, and this reactivity of furan itself is much like an aromatic compound. We do electrophilic aromatic substitution on furan. Okay, another class of ethers that shows unusual reactivity pattern is epoxides. Epoxides are ethers in 3-membered rings. Okay, now epoxides show very high reactivity, and this of course is due to the fact that there's a lot of angle strain in these 3-membered ring ethers. So this gives them much higher reactivity than simple ethers. Okay, so imagine that we have a nucleophile. A nucleophile can approach an epoxide and produce the structure here. Normally we don't think of O- as being a good leaving group, and it isn't normally, but when this O- carbon-oxygen bond cleaves that way, all the angle strain is removed, so this reaction happens here. Okay, we also have an acid-catalyzed variant. So these are going to be the subjects of the next video, epoxide ring opening reactions, and there's a lot of interesting chemistry and trends that go along with epoxide ring opening. Okay, so let's keep